Good morning. In this chapter, Magnetic Effect of Current, Electricity and Magnetism, we already learned that when a charged particle is moving in a magnetic field, it will experience a force. And we also derived an expression for the force acting upon a charge Q moving with a velocity V in a magnetic field B. And we found it as F is equal to QVB sine theta. We also found that if there is current flowing through a wire, a conducting wire, then it produces a magnetic field. And we use Biot-Savart law in order to derive an expression for the magnetic field produced by a straight current carrying conductor. And we found it as B is equal to mu naught I by 2 pi r, where r is the distance separating the wire and the point under consideration. Now today, we will use both these concepts in order to find the force acting on a current carrying wire placed in a magnetic field. And later, we will see the case when there are two wires kept parallel to each other, carrying current in the same direction or opposite direction. Will they attract or repel? So let me share the screen with you and let us start our discussion. So before going to discuss the derivation, I want to make one thing clear to you. Usually, we represent the vectors with their direction. Now, how will we show the direction of a vector perpendicular to the paper or screen? So if you are drawing a vector in a paper, if it is up or down, you can directly show that with arrow mark. And if you are drawing it on a screen, you can also show a vector in up or down direction. Also, if it is towards the right or left, you can show. Now, what happens if it is perpendicular to the screen? How can we represent that using symbols? So let us see what is the conventional symbols used to represent that. See here a dot. This symbol denotes the movement of charges or a vector force directly out of the page. So if there is any vector which is pointed out of the paper, then you can show that with a dot. This is similar to the case when a screw is piercing through the paper and coming towards us. What will we see? We will see a dot, right? So remember this symbol with that. If something is coming towards you out of the paper or out of the screen, you can show that with a dot. Whatever be that, let it be a vector, let it be the velocity of a charged particle, whether it is an electric field or a magnetic field. If it is coming out of the paper or screen, you can show it with a dot. Now, if it is going into the paper or into the screen, this symbol, that is a cross, denotes the movement of charges or a vector force directly into the page. So if there is a electric field or a magnetic field, then you can show it with the cross. Then it means that the field is going into the paper. You can compare that to the case of a screw which is moving into the paper. If it is going into the paper, we will see its backside, which will be a cross, right? So this is the symbol we usually use in physics. Now, sometimes you see that there are a lot of dots. That means in that area, there is either an electric field or a magnetic field which is pointed outside the plane of the paper. So if there are many dots and if it is written capital E, it means an electric field is pointed out of the paper. And if it is marked as B, it means there is magnetic field coming out of the plane of the paper. Now, if you have lot of cross in some area, that means that there is the field going into the plane of the paper. So this dot and cross, dot means out of, cross means into. So you have to know these symbols which are usually used in physics to show any vector which is directed perpendicular to the paper or screen. Now here I have shown you an example. We already know that a current carrying wire will produce a magnetic field. And how can we get the direction of the magnetic field? We have to use here our right hand thumb rule, right? You have to hold your thumb in the direction of the current. So I have held my right hand thumb in the direction of current, that is upwards. Now my fingers curl in the direction of the magnetic field. So when it comes to the right side, when it comes to the right side of the current carrying wire, it is pointed inwards. So it is going into the paper. So that is shown by cross. Now, when I take to the left side, then what happens? This circle will go like this and it is coming out of the paper. So it is shown with a dot. So this means on this side, the magnetic field is going into the paper, and on the other side, the magnetic field is coming out of the paper. So when you have a lot of dot or cross, you have to understand that there is a magnetic field which is moving into the paper or out of the paper depending upon the symbol. Now let us see what will be the force on a current carrying conductor placed in a magnetic field. So this is a simple diagram which shows a current carrying conductor. This is the conductor having area of cross section A and length L, and it is placed in a magnetic field. Here B is shown, and with cross, what does that mean? What is the direction of the magnetic field? The magnetic field is now directed into the paper or into the screen. And then you have the current I flowing through this conductor in the direction shown here. We know that when current flows through a conductor, there will be electrons moving opposite to the direction of the current. So here V represents the drift velocity of these electrons which are moving opposite to the direction of current. How will we find the direction of the force acting upon one individual electron? We have to use the Fleming's left hand rule. So suppose this is my left hand, I have to hold my first finger in the direction of the field. Here the field is into the screen. So I am showing that as into the screen. And then I have the second finger which I will hold in the direction of the current, which is in this direction. So my first finger is holding into the screen, then the current is flowing here, and my thumb will show the direction of the force acting on the charged particle. So what is the direction of the force? Upwards, as shown in this figure. So the magnetic force experienced by a charged particle which carries the current through the conductor is upwards. And you have already learned what is the expression for the force acting upon one electron or a charged particle. Whether it is an electron or a charged particle, it doesn't matter. The magnetic force acting upon one single charged particle having charge Q and drift velocity V. I tell it as drift velocity because that is the average velocity of a charged particle when current flows through that. So Q, V, B, sine theta. Here theta is equal to 90 degree. Theta is the angle between velocity and magnetic field. Here you can see that velocity is in this direction and magnetic field is directed perpendicular to the paper, which is going into the paper or into the screen. So velocity and magnetic field are perpendicular to each other. Therefore, their angle is 90 degrees. So sine 90 is 1. So I can write it as QVB. Now, this is the case of one single electron or charged particle. Suppose there are a total of n electrons or n charged particles inside this piece of conductor. So we have to consider the total conductor because the current is flowing through the entire conductor and it contains capital N charged particles that carry the current. So the total force, this is the force due to one charge. So this is the total force. If there are n charge carriers, then F will be equal to n times the force acting upon one electron. So F into Fm into n. So I have substituted QVB for Fm here. So we get that the total force F is equal to n times QVB. Now, n is the number of charge carriers or number of electrons per unit volume, small n. We have already learned that small n is nothing but the number density, that is the number of charge carriers per unit volume. So the total number of charge carriers in the whole conductor will be equal to n times the volume of the conductor. So the total number of charge carriers in the entire conductor is equal to n, the number of charge carriers per unit volume times volume. And what is volume? Volume is the area of cross section times the length of the conductor. So I have substituted instead of volume AL. So I will get n, the number of charge carriers in the whole conductor. N is equal to NaL. So in this expression for the total force, let me substitute for capital N, NaL. So I got this expression as NaL QVB, which is already there. Now in electrostatics, you have learned that if current flows through a conducting wire, where the charged particles are moving with a drift velocity v, the current I is equal to NaQV. There, if you have considered an electron, you must have used instead of QE, that is the charge of an electron 1.6 into 10 raised to minus 19 coulomb. So here I have used a general case, it can be any charge carrier. Then I is equal to NaQV. So instead of here N, A, Q and V, I am substituting I. So I will get this expression as the force acting on the current carrying conductor placed in a magnetic field is equal to ILB. This is the case when the conductor is placed or the length of the conductor is perpendicular to the magnetic field. And if it is not perpendicular, you will always have this sine theta along and you will get the final expression for total force F is equal to ILB sine theta, or in vector form you can represent it as F is equal to I into L cross B. Now why I have considered the length as a vector? Because I cannot take current I as a vector. We already know that current I is a scalar quantity. So we consider the length of the conductor as a vector having the direction of the current. So F is equal to I into L cross B, or F is equal to ILB sine theta. You will have to memorize this formula. That is the force acting on a current carrying conductor placed in a magnetic field. So the force on a current carrying conductor which is placed in a magnetic field, F is equal to ILB sine theta, which is an important equation which you have to memorize, and you will be using this equation to solve many problems. So this is the method by which the force on a current carrying conductor placed in a magnetic field is derived in your textbook, and I have used the same way. And there is another simpler way to show the same equation. So let me discuss that with you. So here you can see a north pole, and this is a south pole of a magnet, and this is a conductor carrying current I placed in between these two poles, that is in a magnetic field. And here you can see the magnetic field B. In this space, it is directed from the north pole to the south pole. So in this direction. And current is flowing here. And the force experienced by any charged particle will be upwards. How will we get this force? You have to use the Fleming's left hand rule. The first finger pointing in the direction of the magnetic field, and the second finger pointing in the direction of current, and the thumb of your left hand will show you the force, the direction of the force experienced by the charge carrying particle. So here, even if it is a positive charge, here we considered as a negative charge, even if it is a positive charge moving through the stationary wire in a magnetic field, then a single charge will experience a force F is equal to QVB sine theta, the same equation we took here. Then they considered that the velocity is equal to distance traveled by time, right? What is the distance traveled? The length of the conductor, and they considered V as equal to L by T. Here L is the length of the conductor and T is the time taken for a charged particle to move along this length. So velocity is equal to distance by time. And then they considered Q by T. So what is Q by T? The charge per unit time. It is defined as current. So current is charge per unit time. So they have put Q by T as I. So F is equal to ILB sine theta. So whether the charge particle is an electron or any positive charge carrier, the force experienced by the current carrying conductor is same. F is equal to ILB sine theta. So memorize this equation and we will be using that later. I hope this is clear to you. Now let me consider another case where there are two parallel current carrying conductors. Then what will be the force acting on them? So let us see two parallel current carrying conductors. Here this PQ is a infinitely long current carrying conductor. It carries a current I1. PQ is a straight long current carrying wire. RS is another straight current carrying conductor. It carries a current I2 and it is placed at a distance R from PQ. So we have two current carrying conductors, two straight wires which are kept parallel to each other and they are separated by a distance R. One of them carries current I and another carries current I2 and they both are in the same direction. So you have two wires PQ and RS carrying current I1 and I2 in the same direction and they are kept at a distance R apart. Now let us find the force acting between them. Let us take this wire PQ carrying current I1. We know that a current carrying wire produces a magnetic field around it. Now, how will we find the direction of the magnetic field? We have to use our right hand thumb rule. So, I'm holding my right hand here and I'm pointing my thumb in the direction of the current I. So I am pointing my thumb in the direction of current I1 passing through PQ. So my fingers will curl. So when I take to the right side of PQ, it is going in this direction. So when I take to the right side, it is going into the screen. Okay. So here I have shown to the right of PQ B1 into the screen. The cross symbol shows that this magnetic field B1 produced by the current I1 flowing through wire PQ is into the screen on the right side. So what do we have on the right side? Another wire RS carrying current I2. So we just learned that if we place a current carrying wire in a magnetic field, it will experience a force. So FRS represents the force experienced by this wire RS, which is kept in the magnetic field B1. Now, let us find the direction of the force experienced by the wire RS because it is kept in a magnetic field B1. For that, let us use our Fleming's left hand rule. So I'm taking my left hand and I have to hold my first finger in the direction of the magnetic field, which is into the screen. So I'm holding my left first finger into the screen and the current is going upwards. So the second finger I have to hold upwards. So the first finger that is in the direction of B1, which is into the screen, and the second finger which is in the direction of current upwards. Now my thumb is directed to the left. So this force FRS is directed towards the left. How did we get this direction? Using Fleming's left hand rule. So if a wire RS is placed near to a current carrying conductor PQ, due to the magnetic field produced by this current I1, that is B1, it will experience a force towards PQ in this direction. Is that clear to you? Okay, now let us also find what will be the magnitude of this force FRS. We know that the magnitude of the magnetic field B1 produced by a current carrying conductor I1 is given by B1 is equal to mu naught I1 by 2 pi r. Here B1 is the magnetic field produced by PQ, that is a current carrying conductor. I1 is the current in PQ and R is the distance where we are considering this force. So let us consider here B1 is equal to mu naught I1 by 2 pi r. That is the magnetic field produced by a current carrying conductor PQ at a distance r from PQ. Now what is the force? F is equal to ILB sine theta. So what is the force experienced by this wire RS? ILB sine theta. So I am taking here the current in RS. So current in RS is I2. L is the length of the wire. We consider now that both these wires are very long or infinitely long and both of them have the same length L. So I have considered I2L into B1 and B1 is a magnetic field where this wire RS is placed. So the magnitude of the force experienced by wire RS is I2L B1. And there is a sine theta here. But we know that current I2 and B1 are perpendicular to each other. I2 is pointing upwards, right? And magnetic field is perpendicular to the paper. So what is the angle between current and magnetic field? That is the length of the wire and magnetic field. This angle is 90 degree. So I have when considered sine theta here, sine 90 will be 1. So I2L B1. So this is the magnitude of the force. Now for B1, I have substituted mu naught I1 2 pi r. So I got the magnitude of the force experienced by this wire RS. FRS is equal to mu naught I1 I2L by 2 pi r. So this is the expression because I have substitute instead of B1 mu naught I1 by 2 pi r. Mu naught I1 by 2 pi r and I2 into L is already there. So this is the expression for the magnitude of the force experienced by RS. So let us consider the force experienced by PQ because now there are both wires at the same time. PQ will experience a force due to the current in RS, just as RS experiences a force due to the current in PQ. So let us consider the current in RS, that is I2. Again, I will have to take my right hand and hold the thumb in the direction of I2 in order to know the direction of magnetic field B2. Okay, so when I hold my thumb upwards to the left of RS, what happens? The current, the magnetic field is going out of the paper. So it is going out of the screen. So here I have here to the left out of the screen. So it is coming out of the screen. So here to the left I have B2 coming out of the screen. Now B2 is coming out of the screen. And now let me use Fleming's left hand rule for finding the force acting on PQ. So I'm taking my left hand now and I'm holding my first finger out of the paper. So out of the screen, I'm holding it. It's coming towards me, towards my nose. See, it's coming towards me. So I'm holding it like this out of the screen, and then I have to hold my second finger, that is current. I have to hold it upwards. So how will I fold it upwards? So I have to hold like this. Okay. If I hold like this, second finger should be upwards. So, okay, this is the way. So the first finger is holding towards my nose, that is out of the screen. And the second finger or the middle finger is pointing upwards. And now see, the force is in this direction, that is towards this wire RS. So force PQ is now directed towards the wire RS. So we have, from using Fleming's left hand rule, the force acting on PQ due to the current flowing through RS in this direction. Now again we will use the idea of magnetic field produced by I2 at a distance r from the wire. B2 is equal to mu naught I2 by 2 pi r. And again the current carrying wire I1 will experience a force PQ, FPQ due to this wire. And that wire, so that PQ is equal to I1L into B2. Is that clear to you? So the force experienced by PQ is equal to I1L B2, where I1 is the current through this wire, B2 is the magnetic field in which it is placed, and L is the length of the wire. Again, with the same explanation, we can tell that the magnetic field which is perpendicular to the screen and current I which is upward are perpendicular to each other. So the sine theta here will become 1. So the force experienced by the wire PQ, FPQ is equal to I1L B2. Again for B2, I'm substituting this expression. So it is mu naught I2 I1 L by 2 pi r. So mu naught I2 by 2 pi r I have put instead of B2, I1 L is already there. Now look at these two expressions. The force experienced by this wire RS and the force experienced by this wire PQ. They have the same magnitude. Both contains mu naught I1, I2, L by 2 pi r. So both these wires will experience the same force, right? And they are towards each other, which means P1 is pulling RS towards it and RS is pulling PQ towards us, which means they are attracting each other. So if two wires carrying current which are parallel to each other, and if the current are in the same direction, they will attract each other because PQ is pulling RS towards it and also RS is pulling PQ towards it. So they experience an attractive force. Now, we told that this length goes to infinity. In practical case, the length may not extend to infinity, but we can consider them as infinity if the length of the wire is very large compared to the distance separating them r. So if the length of the wires are really large, we may consider them as infinitely long. And r is a small distance separating them. Now here, since we usually don't know the length of the wire, it will be better to consider the force per unit length of the wire. So the force per unit length of the wire, which is same for both, is equal to mu naught I1 I2 by 2 pi r. So you have to memorize this expression. The force per unit length of a wire acting between two parallel current carrying conductors is equal to mu naught I1 I2 by 2 pi r. Okay, so you have to memorize this formula. Now let me consider another case. What difference do you find in this figure and this figure? What difference do you find? I have labeled here the wires as AB and CD. You can see the wires PQ and RS carry current in the same direction. I1 and I2 are in the same direction. Whereas in wires AB and CD, current is flowing in opposite direction. So let us just use the ideas to find directions and see what will be the nature of force acting between them. So first of all, let me consider this wire AB carrying current upwards. Let me see what will be the direction of magnetic field produced at a distance r from AB. So let me use my right hand. My thumb is pointing upwards in the direction of current I1. So my fingers curl in this direction. So when I take a point to the right of AB, what happens? The magnetic field is going into the screen, So I have shown here the magnetic field B1 produced by this current I1 as into the screen. Okay. Now what is the force experienced by the wire CD? Due to this magnetic field B1, I'm just using the Fleming's left hand rule here. So I'm taking my left hand, holding the first finger, which is into the screen. So it's going into the screen. And then the first finger, I have to put it down. Why? The current is moving down here. I2 is down. So naturally, my left hand thumb is pointing in this direction towards the left. So the force FCD, that is the force experienced by wire CD, FCD, you can see is in towards the left. Okay, so force FCD is towards the left. Here we have used both the right hand thumb rule and the Fleming's left hand rule. Now let us consider the magnetic field produced by CD. So magnetic field produced by CD, again I have to use my right hand. This time current is pointing down. So let me put my thumb down and my fingers curl in this direction. So when I take to the right, I can see that again it is coming into the screen. So it's coming into the screen. So I have my right hand, and when I hold here, so to the left, it is coming into the screen or going into the screen. So I have put here B2, that is the magnetic field produced by wire CD. Having a current I2, B2 is pointed into the screen. Now again, I'll have to use my left hand in order to find the force acting on the wire AB. So here, this is my left hand. I have to hold my first finger in the direction of the magnetic field, which is into the screen. And here my second finger, I have to hold it upwards because the current is moving upwards. So you can see what will be the direction of the force. My thumb is pointing to the right, right? So my thumb is pointing to the right. So the force experienced by this wire AB is to the right. Is that clear? So you can see that force experienced by CD is away from AB and force experienced by AB is away from CD, which means AB is pushing CD away and CD is pushing AB away. They are pushing away each other, which means they are repelling each other. So see, when two parallel straight wires carrying current in the same direction pulls each other, they attract each other, while two parallel wires carrying current in opposite direction repel each other. So two parallel wires, if carrying current in the same direction, attract each other, and if the wires are carrying current in opposite direction, they will repel each other. I hope this concept is clear to you. Here, you have to memorize this expression, that is the force per unit length of a wire. If there are two wires carrying current I1 and I2, F is equal to mu naught I1 I2 by 2 pi r. And this magnitude is the same whether the current is flowing in the same direction or in opposite direction. But the force experienced by both of those wires, their direction will be different depending upon the direction in which the current is flowing. If they are in the same direction, they will attract each other, and if they are in the opposite direction, they will repel each other. So that's all I would like to explain about the force acting on two parallel current carrying conductors. Hope it is clear to you. Now let us see, or let us use this expression in order to define ampere. We are using the unit ampere for current for a long time now. You all know that this unit ampere came from the name of a scientist, Ampere, and we learned Ampere's law in this chapter. So let us define what is 1 ampere. And for that, we will use the formula we just learned, that is the force per unit length acting between two wires which are kept parallel to each other at a distance of r and carrying current I1 and I2. F is equal to mu naught I1 I2 by 2 pi r. Now, consider a case where both of the currents I1 and I2 are 1 ampere each. So, both of them carry 1 ampere current and they are kept 1 meter apart. So, the distance between them is 1 meter. And we know that mu naught is the permeability of vacuum or free space, and its value is 4 pi into 10 raised to minus 7. So I have substituted the values mu naught as 4 pi into 10 raised to minus 7 and current I1 and I2 as 1. And then divided by 2 pi, and instead of R, I have put it as 1. So the value of F, pi gets cancelled and 4 cancels with 2, leaving behind a 2. So we get the total force now as equal to 2 into 10 raised to minus 7 Newton. So we know that the force acting between two parallel straight wires carrying current of 1 ampere each, and if they are placed at a distance 1 meter apart, and if it is placed in vacuum, then they will experience a force of 2 into 10 raised to minus 7 Newton. And this fact is used in order to define ampere. So what is 1 ampere? 1 ampere we can define in this way: the constant current which produces a force of 2 into 10 raised to minus 7 Newton per meter length, per meter of length. Why per meter of length? This is the force experienced per length. So per meter of length between two straight parallel conductors of infinite length. We considered them as infinitely long straight wires carrying current while we derived this equation. And of negligible area of cross section placed 1 meter apart, which means R is equal to 1 meter. In vacuum, it's important to mention that it is in vacuum because mu naught is equal to 4 pi into 10 raised to minus 7 in vacuum. This is the value of permeability in vacuum or free space. So it's called 1 ampere. So what is 1 ampere? It's the constant current which produces a force of 2 into 10 raised to minus 7 Newton per meter length between two straight parallel conductors of infinite length and negligible area of cross section placed 1 meter apart in vacuum. So that is how we define ampere, 1 ampere. So what did we learn today? Today we learned how to express the direction of vectors which are perpendicular to a paper or a screen. If it is a cross, it means it is going into the screen or into the paper. And if it is a dot, it means it is coming out of the paper or out of the screen. Then what did we do? We derived an expression for the force on a current carrying conductor placed in a magnetic field, and we got it as equal to F is equal to ILB sine theta, which you have to memorize. Then we use these concepts in order to find the force acting on two parallel current carrying conductors. And we derived the expression that the force between two parallel current carrying conductors per unit length of the wire is F is equal to mu naught I1 I2 by 2 pi R, where I1 and I2 are the current in the conductors, R is the distance separating them. We also use our thumb rule and Fleming's left hand rule in order to find that if the currents are passing in the same direction, the wires will attract, and if the currents are flowing in the opposite direction, they will repel each other. And we use this formula to define 1 ampere. I hope this is clear to you. So let me end this video here.